Hello everybody and welcome to the second part of this little series where I tell you my ways of going about preparing a good scholarly presentation. Now in the first part I went over my tips on how to prepare the actual presentation, and in that part I mentioned that I might record my practice talk or my actual talk to show anybody out there how it actually went. And even though I got the footage for that,
the last requirement is more of a practical one, and that is that in order to make use of this excitation energy coming from Singlet Phishing process, we must be able to separate our correlated triplet pair and further be able to separate our individual triplets to harvest that energy.
now, I've debated a lot whether or not that footage is going to make a useful video. My main concern being that I'm not sure if anybody out there watching this has half an hour to spare to watch me blab about this topic of singlet fission, and then another half an hour to watch me answer questions on that topic. Again, given the fact that this topic of singlet fission may likely have nothing to do with your research at all. So instead, to kind of compromise and still make a useful video, I've decided to go over my slides in a lot more detail and show you how I was using various visual aids in order to reinforce ideas I was saying verbally during my talk. So I'm going to go and hook up my laptop to some kind of screen capturing software, and I'll try to keep this as short as I possibly can while still making it useful. And hopefully it's all going to work out, since right now I'm enjoying my favorite beverage of choice, which is a good old chestnut ale. I wish this was sponsored content, but it's not. Alright, so here we go. In case anybody's wondering, the way I'm recording this is by using this little screen recording option in PowerPoint, surprisingly. So that's pretty convenient. So let's go over the actual slides. Now, right away to start off with, I have the title slide with a nice little picture, which I took myself, totally bragging rights worthy. But right away, this is something important that I wanted to bring up, and it's the subtle details. Now, my talk is about photovoltaic devices in one shape or form, and in case you don't know, photovoltaic devices essentially are your solar cells. So what I'm talking about is sort of utilizing the green energy sources. And in this image, if you pay close enough attention, you see a bunch of windmills for capturing the wind energy, and of course you see the sun. And this isn't like a make or break point for your presentation, but I think giving a talk from the audience perspective, it's a lot about psychology. And you know, with this image, if you don't notice that in this picture you have the windmills and the sun, then you know, you just wouldn't mind. You would think, well, this is a nice image that you can look at for the beginning of the talk. But if you pay close enough attention to details, if you're just that kind of person, right away you would kind of be positively engaged and positively set for listening to this talk, because you would connect the dots and think, oh, well, this is a talk on photovoltaic devices, and well, this picture is somewhat relevant to those photovoltaic devices. Anyway, it's just little subtle details which you shouldn't completely ignore when you give the presentation. So right away, when the previous speaker introduced me, the game is on, the time started, and I started talking about my presentation. And on this cover slide right away, I essentially started setting the stage of what I'll be talking about. Pretty much, I've said exactly what I just told you, that my talk will focus on the ways to utilize so-called green energy resources, and in particular, utilizing the solar resources. And I knew that my audience are a bunch of chemists, so I made a point that looking at solar cell efficiency, looking at how to improve our ability to capture the energy of the sun, is really an interesting topic for chemists to look at because it requires looking into new material designs. So, right off the bat, even before beginning the presentation, I'm starting to set that stage. Okay, moving on. Again, the first slide is titled Harvesting the Energy of the Sun. And as you will notice as I go through these presentations, all my slides start with a blank sheet of paper, in a sense, with just the title. And the reason for that is because I strongly believe that when you're given a talk, you should approach it from a perspective that you are the main focus that the audience should pay attention to. It's not your slides. Your slides are simply there to reinforce things that you're saying. So by starting off with a blank slide with audience having nothing but the title to look at, I am essentially forcing them to look at me instead and listen to what I have to say before I pull up some images to reinforce those ideas. So in this case, the first thing that comes up on this slide as I start talking is a diagram of a photovoltaic cell. It's a good introduction to get everybody on the same page about what a solar cell looks like in terms of kind of the diagram and the chemistry that goes in it, and to reinforce the solar cell again idea as I'm speaking during my presentation. I have this little sun pop up and the light bulb light up to again just give a visual aid for people to really get on the same page about the topic of solar cells. I go on and talk about the amount of energy we receive from the sun on the surface, and then how efficient we are at capturing that energy. And as you see, again, with every point that I'm making, I don't have it appear on the slide right away. I force it to appear on the slide when I get to that point. That way, the attention of the audience is not to wander around the slide and try to read things on the slide before I talk about it. That way, people will just, concentrate on reading instead of listening, and they might miss the point that I'm actually wanting to say if it so happens that my slide is busy and it's easy to kind of start wondering in your own head of what's happening there. Anyway, moving on from our solar cell efficiency, I go on and talk about the so-called Shockley-Kaiser limit, which is the inherent limitation of our ability to capture and harvest the energy of the sun. And again, as I talk about it to really reinforce the point that I'm making, I make a little red box pop on the screen which highlights the Shockley-Kaiser limit. It's about the little subtle details that you include in your slides that are going to work together with what you're saying and reinforce those ideas. At least that's what I believe is the whole point of having this PowerPoint in the first place. Otherwise, we might as well just listen to a lecture. So, furthermore, talking about the Shockley-Kaiser limit, I briefly go and explain where that limit arises by having the solar spectrum. Again, I know that my audience is an audience of physical chemists, so I expect them to be familiar with this spectrum to start off with. And, I'm not spending a whole lot of time explaining what's going on here. It's just a brief reminder of where the Shockley-Kaiser limit comes from. And again, as you notice here, the audience may be looking at the numbers where the energy losses originate from, where we get this 33% value. And I really, again, want everybody on the same page as I'm giving an introduction to what these numbers mean. And these numbers refer to the power conversion efficiency, which comes up throughout my talk later on. So I thought it's important to pull it up right away and get everybody comfortable with what the power conversion efficiency is. And I spent a very little amount of time on just briefly defining verbally what it is and having this equation pop up as I'm doing this. Now moving on to the same slide, to the next slide. Again, start off with the blank slide, and I say that at this point of the presentation, I'm actually saying that I want to create a mental picture for the audience so that they get a sense of importance of my topic. So to do that, essentially I pull up this picture and I verbally say that I went ahead and found out how much of the surface of the Earth we would need to cover in solar panels in order to power the world. And this picture, which I just found by Googling, a photovoltaic farm or a solar panel farm, something like that, that's the mental picture I want my audience to have. So I pull it up. And with using pictures off of the internet, it's kind of a debatable topic whether or not it's appropriate to do so. I think it's not a huge deal as long as you acknowledge the source where you got the picture from. So for instance, here I used this fortune.com website, which just popped up on Google to give me the stock kind of looking image. For any images that I made myself, I never reference them. And if a question arises, it's a fair game. If I took a picture, I don't think I am by any means required to reference it. It should be assumed that if you don't reference something, it's your work. At least that's ideal world. Anyway, but it's good practice to keep track of all your references, even for small things. At least you won't get in trouble for doing that. So I set a mental picture for my audience to have with the solar farm, and I go ahead and pull up a map of Canada, as I'm from Canada, and I draw a few squares with the area we would need to cover of Alberta, since, again, I'm from Alberta, and the little dot here is Calgary, with having the area we would need to cover in the solar panels with current efficiency that we can harvest the energy of the sun at the Shockley-Kaiser limit, which is that upper bound limit, which I've already mentioned to the audience before. And then, here is the catch, here's where I make the transition to the next thing I want to talk about, and that is kind of the dream big scenario where we harvest the energy of the sun by overcoming that Shockley-Kaiser limit, right? So essentially in previous two slides, I've made it very clear that this limit, whatever it is the fundamental limit above which we cannot harvest the energy of the sun. And then all of a sudden, two slides later, I introduce the idea of overcoming that limit, right? So it may sound like a contradiction, but it's a contradiction that is made on purpose. It is made to draw attention of the audience to the topic that I'm presenting. That, some ideas that we've had about harvesting that solar energy may no longer hold 100% true, or we found out some ways to overcome the limitations that originally we thought we had. So that immediately kind of transitions to the next thing I want to talk about, and it draws attention of the audience to the points I'm trying to make. So obviously the next slide is, can we actually go above the limit? And here I just have a bunch of screenshots pop up from journals that I've skimmed through about overcoming this limit. And the area that I concentrate on in this particular image with these particular titles is so-called multiple exciton generation. So I bring this up kind of out of the blue the audience has no idea what this is yet, but hopefully they're interested to learn more, as again, I just gave them a justification for why that limit exists, and now I'm saying, well, actually we can go around it. So immediately the audience should kind of be interested in what I have to say. That's the idea, at least. Again, without changing the title, I'm still talking about going beyond that Shockley-Kaiser limit. And the first thing I do is to explain what this multiple exciton generation is. And here I'm just using a very simple kind of corny diagram to show what it is. We have a photon arriving from the sun into this magician's hat, and we get 2 electrons out of the hat. And essentially I talk about the efficiency of this process being 200%. So for 1 photon that we put in, we got 2 electrons out. And I also mentioned that this efficiency does not refer to that power conversion efficiency, which we talked about, which again comes up later in the slides, where I again draw some parallels between, or I compare and contrast these 2 values. So right away I'm going to make sure the audience knows the difference between the 2 values that I later on present. And I highly encourage you to make these simple diagrams. Honestly, it doesn't take much time. Again, for the image of the magician's hat, I just found it on Google and I referenced that, so there should be no problems with any copyright kind of deals going on. So yeah, I find this a very useful way, and it's all about drawing attention of your audience. When you make something yourself, and even though, you know, this by far is not the best piece of art that you're going to see in your lifetime, it still draws attention of the audience, even for a simple fact that it's pretty obvious that this little animation was homemade. And I think it's always appreciated when somebody goes through the effort to make these things, to again just make the point clear about what you're trying to explain. So coming back again to the image I had presented before, now I verbally say that, well, now we know what multiple exciton generation roughly represents. And then I go on and make another transition to my actual topic, which is singlet fission. And again, I just have a quick snapshot of another paper title, which highlights that singlet fission is an efficient multiple exciton generation process. So again, I kind of closed off that box of talking about multiple exciton generation, and I opened up a new box of singlet fission, which is my actual topic. So at this point, the introduction is sort of done, and I move on to explain the details of what I did research in to prepare this presentation. So again, the first slide, absolutely blank, except for the title. Here I say that let's take a look at singlet fission process from the physical chemist point of view. And the way to do that is to look at energy diagrams. And so I have a quick animation showing the energy diagrams and what happens during singlet fission process. Again, for the sake of this little video, there is no point of me to go and explain what these diagrams represent, apart from the fact that hopefully you see that they're quite simple. It didn't take me a whole lot of time to make these in PowerPoint. Yeah, I mean, use diagrams as much as you can. And one thing that I guess is worth highlighting is whenever you make diagrams, you have the ability to make your own diagram or your own animation. You might as well make it as big as you can. Right, again, it comes back to something I talked about in the first part of this series, which is that you want to make sure everybody in the room sees what you're showing on the slide. So whenever you can, magnify all your figures and images to the max. It won't hurt ever. Nobody's gonna come back at you and say your diagrams are too big. Rather the opposite, if your diagrams are too small, it's just going to be super annoying for the audience to squint their eyes and try to understand what you're showing. Anyway, pretty self-explanatory things. So after I showed the singlet fission diagram, kind of bringing that sense of what the process is to the community of chemists that I'm presenting this to, I go over again, reiterate the requirements for this process to happen. Even though in the previous slide, while I was showing this animation step by step, I was verbally talking about the requirements needed for this process to happen. What I really want to do, again, is to really make sure my audience has a good sense of what this process is all about and why it's interesting to talk about and it's interesting for them to listen to. Why should they keep listening to my talk when they can just daydream and mind their own business? So again, reinforce that thing. I'm not spending a whole lot of time here, essentially because I already verbally talked about these things. But if you followed through me clicking through the various things appearing on the slide, you saw the three things appearing, while at the same time on the different representation of the energy diagram, a few things would pop up, essentially highlighting what I'm talking about. And then the last thing, which again, I find it just helps the audience follow your talk, is to really make it simple for them, right? My talk goes on to talk about why having the singlet fission process is difficult. I don't verbally say that, of course, but I want to make it easy for my audience to know what I mean by easy and difficult in the context of my talk. So I very simply just say that, out of these requirements for singlet fission to happen, satisfying the first two is an easy, in quotation marks, task. That there is a lot of molecules that can do this. However, it's satisfying all three requirements where we actually make use of the energy we get from singlet fission, which is represented by this third point. That's what's actually difficult. So it's not a matter of finding molecules that can do it, it's a matter of finding a combination of techniques and combination of molecules in a device. That's the difficult part. So again, make it simple for your audience to know what are your own criteria for calling something easy and difficult. Don't make this a mystery novel by any means. This should be a scholarly presentation where, it's cut and dry, to some extent boring. You chew everything for your audience, especially in a talk setting where, once they saw a point pop up on a slide, likely they won't see it again. So you want to make sure that they really paid attention to that point if you think it's something very important. Okay, moving on. So in the slide, again, I've established what I consider is easy and difficult for my audience to have some sense. And then I go on and say that, well, even though satisfying all three things is difficult, there's been some examples, and it's with using these particular molecules, acenes, which undergo this process of singlet fission and make the utilization of this interesting chemical photophysical property of these molecules viable. So again, I showed a molecule of typical acene, and then I say that the reason why they omit kind of the difficulty of general singlet fission materials is because they have this stacking in crystal form, so I simply switch a diagram to show a different form, a different point of view of these molecules, to reinforce the idea of kind of right away why these molecules work for this process. Cool beans. So, I go on and talk about making use of singlet fission. Again, from defining what it is, the next logical thing is, well, how can we actually make this useful and gain something from performing this process? And essentially in this diagram, without going too much into detail, the first thing that I bring up is essentially we have to think of an incentive for the electrons to travel through our circuit in order to generate that power, being this photovoltaic cell. And to do that, we need to think of the different materials that we use to couple the process of singlet fission with generating free charges to travel through the photovoltaic cell. And this is my first kind of research paper that I thoroughly discuss. And at this point during the talk, I verbally start saying names of the authors whenever I refer to the paper. This way, the audience kind of gets a sense that this is something important. Before, I would just generalize the points that I brought up, even though references did pop up on the screen. I didn't pay particular attention to them. Here, once I brought up these diagrams, I literally say Jadaf and colleagues were interested in finding the appropriate material to make singlet fission work. This way, the audience knows that, all right, well, the work by Jadaf is something important, and it's something they should pay attention to. Again, little things, but I think they make the talk a lot easier to follow overall. And once I discuss the idea of building a solar cell, and I discuss about creating an incentive for electrons to flow in this diagram, essentially I move on and make another transition to actually talk in a bit more detail about the Jadaf's paper. And I bring up this little point, which simply states that by considering the energies of their singlet fission materials, they thought of an ideal range to look for the acceptor material, which is going to make the whole solar cell operational. So moving on to discuss the work by Jadaf and colleagues, I talk about the molecules they use to perform singlet fission, and I talk about the diagram and why it's relevant to the process here. Those are simply energy levels of the two materials in this particular case. Without going too much into the chemistry for this video, again, I do the same thing for acceptor molecules. I talk about what was the judging criteria for the devices made by Jadaf. Essentially, how did they know that one combination of these materials, so one donor with one particular acceptor, was better than another donor with another particular acceptor? And essentially, they used this external quantum efficiency, which, again, for the sake of this video, doesn't matter. And after I've defined all the variables which are important to understand the results of Jadaf, I pull up the image of the actual results. And here I explain that this pentacene C60 combination worked the best, and the reason for that is due to energy alignment between this highest energy level of C60 and the center, the middle point between the energy levels of pentacene. And again, because I know my audience are chemists, I go on and make an assumption that they gather why this actually lines up in the middle. And I verbally say why that is. Again, I'm not going into detail for the sake of this video. Something that is very important though for the presentation is, again, the appearance of the figures. Now, as you can see, these figures are huge, and it took me a little bit of effort to make them look this way, because originally, I'm just going to quickly show you. Originally, these figures, this is the original figure from the paper by Jadaf, which I just took a screenshot of. And as you can see, there is so much going on here, right? I mean, if I pull up this figure, I will spend like 5 or 10 minutes just talking about what these different materials are and the reason why certain things were tested, and it's just going to take way too long. So instead, I remade that particular figure in a way that is supporting my talk, right? I only care about presenting really this particular combination of donor-acceptor molecules. So this is the only thing that I talked about from the paper by Jadaf. And verbally, I don't think I actually did it in a talk, but if you feel like that's necessary, if you end up doing something similar, you can verbally always just say that this is just part of the work that the authors did. However, this is the part that is most relevant to the points that you want to make in your presentation. So, anyways, go through the trouble of reworking those figures. It's going to save you a lot of grief when you actually present. And again, from audience perspective, this is a lot of material to look at on the slide. But again, I'm utilizing as many tools as I can, such as making things appear sequentially. Only when I start talking about a particular point, I made that visual aid appear on the screen to reiterate that point, right? And again, making the figures as big as possible so that nobody has to really work too hard in order to see what's actually on the screen. So from presenting the results of Jadaf, the next question that I ask is, well, how do these authors know that the process which they were characterizing is actually singlet fission? I mean, there is a lot of things that could have went on, and we would like to have some kind of confirmation for that process to actually happen, right? So anyway, I explain the experiment which Jadaf and colleagues did in order to confirm that. Again, kind of, if we just go back a couple of things, I present the energy diagram again. This is something that I keep coming back to throughout the talk in one shape or form, so the audience has something familiar to look at. Right, when I switch gears, kind of, they don't feel completely lost. Again, at least that's the hope. So I always bring up kind of the energy diagram to start with. Again, remind them what the process we're looking at actually is, without having to spend too much time on it, right? Because I already talked about it. Just a reminder. And then I go on and say, well, if we perform the experiment, in one particular instance, we would have one outcome of the experiment. In another instance, we would have a different outcome of the experiments. And based on whether or not one thing or the other happens, we can make some kind of connection. Chemistry things. Let's not get into details. So, yeah, I reiterate that when the field is on, so to speak, this process doesn't happen. So, after explaining what the experiment is, I again just pull up the actual experimental results from the paper by Jadaf again, and I say that, well, this is what we expect. Those are expected outcomes for singlet fission process, and this is the opposite outcome, which means that singlet fission process in this particular material does not happen. So anytime, this is also something very important. Anytime when you start explaining your results, I think it's super important to explain what the graph is actually showing. So in this case, while I was explaining this whole thing, I kept talking about the change in photocurrent. So when this little graph pulled up and the audience saw the change in photocurrent, they know that it refers to something that I just talked about, right? And the magnetic field, which is the experiment again, which I talked about during the explanation of this set of diagrams, right? And literally, when you present your results or present results from a paper, just verbally walk your audience through what is happening here. As we turn up magnetic field, the DPP pyrrolidine CN2 combination of materials seems to have a decrease in their photocurrent generating ability with increasing magnetic field, which is what we expect when singlet fission process happens, right? It only takes about 15 seconds to say those few sentences in this particular slide, but you're just ensuring that nobody in the audience gets lost by what you're showing in the graph, right? It never hurts to reiterate ideas, especially when it only takes 10-15 seconds to do so. Spare that time, and somebody in the audience will internally thank you for not leaving them behind in case they miss something in your explanation of the experiment prior to. So from looking at these results so far, I go on and say that, well, based on this data, we can see that the most promising system is a combination of this pentacene C60, which is shown on this fancier looking diagram here. And I go on and say that, well, this work was picked up by another group of researchers who really sought after to optimize the design and make this function at the maximum efficiency that it possibly can. Now, take a notice, I guess, here as I switch the slides. This is something neat that I saw somebody else do, and I picked up this habit myself. When I really want a smooth transition, such as in this case, when I still talk about the same system, the same kind of core I just had a brain fart. Sorry. When I still talk about the same kind of core concept from one slide to the next, one neat thing that you can do is to have the diagram stay in the same place. And it's really easy to do. But this way, the title has changed, and verbally, hopefully you've made the transition to talking about a different piece of work or whatever it is. But the audience kind of subconsciously still is on the same page of the core thing that you were talking about, which in my case was the system of pentacene C60 materials. Anyway, a neat trick. Use it if you like it, but I find it neat. So I start talking about the state of the art again while I verbally mention that this work was picked up by another group, etc., and they wanted to optimize the design. So I pull up at yet another representation of the energy diagram, and every time I do this, I always say that, again, we're looking at the exact same thing that I was showing before, just in a different representation. And this kind of serves a dual purpose. Again, it ties, you make sure that the audience follows your talk, but it also kind of teaches your audience, for whoever may not be familiar with the topic, about the different ways, if they get interested in this topic, about the different ways they might see data and diagrams represented depending on what papers they read. So, I mean, the point of a presentation is in some way to teach somebody something new about your field of studies. So, I think that serves a purpose. But again, I mean, I could have used the same energy diagram I've had before and potentially avoided the risk of somebody getting lost at this more confusing looking diagram here. I guess I chose to use the more confusing looking diagram, but yeah, cool. And then I say that one of the main things that the authors looked at is the width of the pentacene layer. And even though I know that Congreve and colleagues looked at a whole whack of things to optimize the system of pentacene C60, and they got their paper in Science, which is the top tier scientific journal out there, right? So even though they looked at a whole bunch of things, I don't particularly want to bring up all the things in this paper. I really just want to make a point about one particular experiment that they did, so I only mention that. Again, moving on to talk about the experiments of the state-of-the-art system by Congreve and colleagues. I pull up the experimental data that was presented in a paper, and I explain what the authors looked at here. And to transition to the next kind of set of experiments, I pull up this rather complicated equation. And the trick with equations, unless you're presenting perhaps for a math inclined audience, which my case was not that case, the trick with equations is to right away, as soon as you pull this up, to tell your audience that they shouldn't worry about this equation. That this equation simply shows whatever it is that you want to make a point about, right? It's kind of neat to see the equations, right? I mean, for the audience of physical chemists, I kind of expect them to be nerds and to find looking at these equations interesting. Maybe some of them are going to understand more than others, but really, verbally, as I pull this up, I literally say, do not worry about this equation. It looks rather complicated. The only thing this tells us is that by finding the value of x, we can find the quantum yield of singlet fission. Whatever that means, in case you're not sure what it is. It's totally okay. So, right, so anybody out there who can follow this equation, you know, they won't mind that it's here. But for probably majority of people in the audience who couldn't care less about looking at this equation, they will appreciate the fact that I say, what exactly are we looking for in this equation here? So, after I kind of briefly explain the equation, I pull up the data that was obtained from the first set and transformed using this equation into the second set to give us the next point that I talk about. And lastly, I pull up the next set of data to kind of finish talking about whatever it is I want to bring up with respect to the paper by Congreve. Again, to reiterate the point, I talk about this new quantity, which the audience hasn't seen before, which is the internal quantum efficiency. I want to make sure everybody understands it, so I just have this pop up on the slide in case anybody gets confused about it. And then I focus the attention of the audience on just particular area of this data, and I explain how this data is creating a controversy. That one set of data is telling us that the device operates at the maximum efficiency it possibly can, which is here, while this set of data tells us that, well, in fact, the efficiency we actually see on the receiving end of the device is not the same. Here it's 200%, here it's around 150%. So by pointing this out to the audience, I make another transition to the next point I talk about, and essentially that has to do with kind of what happens to the free charges we generate from singlet fission, in this case, after the actual process. Right, so essentially so far in the talk, I've went through defining the process of singlet fission with some examples from the literature and some state-of-the-art, to now talking about, well, what happens then, right? That's another transition. And briefly, I bring up a point, which I later on reference in my talk a few times, that the work by Politaev from the Richard Franz group found out the reason for the discrepancy in this particular set of data. So I close off this Pandora's box to open now the next Pandora's box. So I bring up the slide that we have seen before, again kind of recalling something familiar that the audience has seen. And essentially here, where I was talking about the process being easy versus it being difficult, I go back and say that now that we have seen some discrepancy in the data, we have to question how easy or difficult this process actually is. And some people saying that, well, we need to scratch this material to find new ones, while other people saying that, well, actually no, we already know that that material does satisfy the requirements fairly well. We just have to sort out one little detail in the design of the device. And this is something that I started doing just recently, having kind of this homemade, like really homemade, hand-drawn lines appear on the screen. And again, it's just something different for the audience to look at. And the way I did this is just, I got a touchscreen laptop recently, and I thought, well, it would be fun to actually draw on it and include that in my talk. And I think it went very well from the audience reception. So the first thing I talk about is new materials. Again, going back to the previous slide, this is one of the points which I brought up on this slide. New materials. I again kind of have a similar format energy diagram which I have used before, and I talk about the energy requirement for singlet fission being difficult to satisfy for this particular type of molecules, but being potentially easier to satisfy for a different kind of molecules. Details, I guess, for the sake of this video, don't matter too much. And again, I have all of these diagrams are homemade, by the way. Like I just made them in PowerPoint, right? And I highlight that, well, some work has been done by Nakano's group, which has shown that there is an ideal range for these new biradical so-called molecules to actually undergo singlet fission, right? I make it easy for the audience to follow the points I'm trying to make, hopefully. So I go on and talk about some developments of new singlet fission materials. Again, doesn't matter too much. I don't spend a whole lot of time on that. And then I come back again to the same slide, which the audience has seen before, for the sole purpose to just remind them that there were two things to solve the issue of singlet fission, or to look at potential solutions. One was new materials, which I just covered in the two slides before. So now I'm going to talk about the kind of the second side of the coin, which is looking at the Exciton extraction. Don't worry about what that means. So for that particular point, I talk about so-called intramolecular singlet fission, which uses conjugated dimers of molecules. So essentially, two of the same molecule connected through some kind of connecting piece, right? So again, I explain things to the audience. I explain why one of these molecules is better to study than the other one, and I base my arguments on the crystal structure of these molecules. And one of the last things I do is explain another experiment which was done to probe that intramolecular singlet fission that I just brought up. Essentially ask my audience a question, not for real, but kind of a question that I answer myself. A rhetoric question. There we go. I ask my audience the rhetoric question of, well, how can we find out if singlet fission happens in this material? And I go through the experiment that we can do and monitor the population of different species as a function of time, and that there exists an instrument that allows us to look at the population of molecules in the different states. And I have a little animation which I made that while I'm explaining all those things, I play in the background. So for the sake of this video, we won't worry about the details, but yeah, the bottom line is, making things appear at the right time as you verbally talk about them, and also having, things like color coding and just little details. They also help audiences follow what you're saying, right? So here, even like, I'm not sure if anybody noticed this, but I feel like, again, on some kind of subconscious level, this maybe helped somebody. This green part here is also green here, and it's also green on this diagram here, right? So one might think that all these three things are kind of part of one picture, which they are. Same thing with yellow here, and yellow here, right? So even if somebody didn't catch my explanation while I was blabbing about this, hopefully at the end of the day, just by looking at the diagram, they were able to make some kind of connections in as simple things as color coding. And last thing I do is talk about the last few results that I wanted to present about these intramolecular singlet fission models, work done by Korovina and colleagues. I go on to explain the data, and in the previous diagram I explained how these experiments were done. So here my job is much simpler. I simply say that this is the data they get after performing that experiment, and they were able to show the following kind of conclusions. One of the things that I wanted the audience to pay attention to, I highlighted in a different color, and I made the last diagram pop up, which kind of, with respect to this point which I highlighted, um, made the audience think about what is actually happening based on the data that I've explained from the paper by Korovina. Anyway, and that pretty much concluded my talk. And the last thing I did was to have a summary, conclusion / forward-looking statement, all squished into one. The reason I did this is because I knew my talk was pretty tight on time, so I decided to talk about summary and conclusion and forward-looking statement all in one slide, and I think it worked fairly well. I highlight the things that we've learned from my talk and potential improvements and kind of the future work that needs to be done in the field in order to target some of the issues, such as the low power conversion efficiency, triplet diffusion, and things like that. I draw this line in order to indicate that I'm done with talking about intermolecular singlet fission, because now the audience has also seen intramolecular singlet fission, which is different. So I go on and just briefly mention that I talked about some potential new materials and how we might be able to find them. And lastly, I talk about the intramolecular singlet fission, highlighting a couple of things which I mentioned while I was verbally presenting that part of the talk. And again, have a diagram as kind of what is the next step, and explain why I think the next step for this instance is to test these materials in bulk heterojunction type devices. And the very last thing on the slide, which is not done yet, is on the very bottom. This reference appears, and I verbally mention to the audience that kind of if they want to find out more about this topic, this is kind of the literature that I recommend. Like if somebody was dying to learn more and they only had time to read one thing in the literature, this is the thing I would send them to. And I find it it's a nice way to conclude your talk and to give audience some kind of sense of professionalism, that you care about them learning what you presented. So I go through my acknowledgement slide. This is my wonderful group, by the way, so good deal. And the last thing that I did here, I didn't actually go back to the slide. This is the next slide after the acknowledgements, and it's the same conclusions and summary slide. And at this point, I tell the audience that the talk is over and that I will keep the summary and conclusion slide on the screen during the question period in case somebody wants to ask a question about the different parts of the talk, right? And if they're thinking about a particular question, but they weren't sure if I maybe I explained that part, having the conclusion and summary slide during the question period just on the screen, you're kind of just helping the audience with their question, and you're helping yourself by avoiding any silly questions that relate to something irrelevant that you didn't talk about at all, or whatever it may be, right? Make your life easier, and it also looks good on you for doing it. And that's it. That's the whole presentation. Hopefully you found this somewhat useful. I'm sorry about the amount of chemistry. If you hate chemistry, which I can't blame you for, if you sat through this, thank you very much. And I genuinely hope you find some of this useful. The very last thing that perhaps is worth mentioning is that after all of my slides, I have this black slide there just in case I, overshoot in terms of pressing the buttons and go from the very last slide I intended onto the next one. Then it has nothing on it and there is no questions. It doesn't look weird or anything like that. My advice, do it if you feel comfortable. I certainly do. because at the end of my talk, I also have a few extra slides in case the audience has questions about it. So in this case, I have a little bit more detailed of a slide in terms of that intramolecular singlet fission probing that I've talked about during the talk. I thought that was while I was preparing the talk, I thought that that was probably going to be the most difficult slide to get through for the audience who doesn't know anything about performing this experiment. It is fairly specific to uh, the photophysics and the photochemistry community. I also have a slide, an extra slide of experimental results from Jadov and colleagues, just in case anybody asks, well, what else did they do, or did they look at some other systems? Then I can quickly pull up the slide, and it will look super cool and professional for me to say, well, yeah, actually I looked into it, and this is some other work that they did, and this is what they found out. And, you know, I think that would be awesome if that were to happen. And again, that diagram, just to remind you, I made from a rather complicated looking diagram to reinforce things that I wanted to concentrate on. I also have this extremely messy slide, but when it actually plays in the presentation mode, essentially I can make it look a lot more manageable. And this slide talks about the actual, I guess, a question of whether or not these devices can actually power a battery, which is again a question that I thought potentially can come up, and this would be a way for me to explain that with a visual aid. And the last thing is, again, in case somebody asked about new materials, I had another slide on some work that was done on using new materials for singlet fission, because I knew that during my presentation, I really briefly brushed on new materials. I didn't present any results for this, so I was prepared in case somebody was wondering about that to have some results. And this slide is essentially the same thing. Again, it looks messy, but it plays fine in the presentation mode with things that I actually would explain in case that question popped up. So, well, that diagram doesn't look like it's in the right place, but nobody asked that question, so all good. And yet another slide on different materials. Again, essentially all the different things that I thought potentially would get asked that would require me or would help me a lot to have a visual aid for the audience to follow while I explain. Okay, so thank you all, ladies and gentlemen, for listening and looking at this, if you've made it this far. I will make the third part where I reflect on giving this presentation. At this point, I've already given this presentation, and I can give you a spoiler that it went very well, but there were a few things that I think I can improve on, and I'll cover that in part 3 of this little series. So stick around if you think that might be useful. And for now, I'll see you next time.